Hello and welcome. In this second lesson, we are going to talk about quantum physics and radioactivity. Quantum physics and radioactivity. We are going to be solving past WAEC and JAMB questions on this topic, quantum physics and radioactivity, and we are going to focus on calculations only. So for theoretical part, you can read that part up. Alright. Now we are going to discuss the following. We'll talk about energy of a photon, energy of a photon, you have to read about photon, find out the meaning of photon, what we call photon in physics. It is under quantum physics. Now, the wavelength of a photon, how can we calculate the energy of a photon? How can we calculate the wavelength of a photon? How can we calculate the frequency of a photon? And how can we calculate, we'll talk about alpha decay. We talk about alpha decay. We talk about beta decay. Then we also talk about half-life, how to calculate half-life of a radioactive particle. And then we talk about energy level differences, energy levels. We'll talk about energy levels. Okay, so let's get started. In quantum physics, energy is said to be quantized. What it means is that energy can have specific value. If we draw the shells of a particular atom, each shell represents an energy level, and quantum physics is telling us that each of the shell can only have a particular amount of energy that can exist within that shell. The energy is not continuous, it is discrete. It has a particular value. Once you move from level 1 to level 2, you know that the energy within that level 2 is this. You move from level 2 to level 3, the energy within that level 3 is one particular value. So the energy here within this shell, the energy around it remains the same. For this one, the energy around it remains the same no matter the position the atom is found within this particular shell, because every shell has a particular energy that it contains. This is the discussion of quantum physics. That is what this thing is telling us. But our focus is not on this theoretical part. Our focus is on calculation. How can we calculate the energy that each shell contains, or an atom that is found in a particular shell? How can we calculate the energy that it contains? That is the energy of a photon. To calculate the energy of a photon, we use this formula. Energy is equal to energy of a photon is equal to hc over lambda hc over lambda. That is hc over wavelength, where h is called Planck's constant. Planck's constant. It is constant. It is a constant value. The value of this h is always given as 6.626 times 10 raised to power minus 34. H is always equal to times 10 raised to power minus 34. So wherever you see H, you put this value there if you want to calculate the energy of a photon. Now C is the speed of light. Speed of light is also constant. In physics, we know that the speed of light, which is C, is always equal to 3 times 10 raised to power 8 meter per second. So C also is constant. 3 times 10 raised to power 8 meter per second. Now, so in this formula, what the unknowns here are always the energy and the wavelength. We can be asked to calculate the wavelength or to calculate the energy. Now, this energy can also be expressed in another form. Note that when we discussed wave, we said that velocity of a wave is equal to wavelength over time. And we established that time is equal to reciprocal of frequency. So we also established that velocity is equal to wavelength times f, because 1 over t is equal to f. So we use f to replace 1 over t. So what it gives us is that velocity is equal to f lambda, that is frequency times wavelength. Now, if we make f the subject, it means that f is equal to v over lambda. F is equal to v over lambda, that is v over wavelength. where v here is velocity. But in the case of this photon, or in the case of light, which is part of what we are talking about, photon, it falls under our discussion here. V is represented with c. The velocity of light, instead of writing v, we use the symbol c to represent the velocity of light. So when we are talking about light or photon, then we have that F is equal to C over lambda. F is equal to C over lambda. Now remember that in this formula we have that energy is equal to hc over lambda. So we cannot say that since energy is equal to hc over lambda, this formula can be broken down into its components, which is h times c over lambda. Now what it means is that energy is also equal to h. We now use F to represent this c over lambda, since we have established that frequency is equal to c over lambda, which is velocity over wavelength. So we have that energy is also equal to hf. So these are the two formulas for energy of a photon. Depending on what is given to you, you use either energy is equal to hf, or you use energy is equal to hc over lambda. So in questions you are going to see about energy of a photon, you can be asked to calculate energy, or you can be asked to calculate wavelength, or you can be asked to calculate frequency. So when you read the question, you see the parameters that are given to you, then you know the formula to use. Now let's solve an example from a past question. This question says, calculate the energy of a photon with a frequency of 6.0 times 10 raised to power 14 Hz. Calculate the energy of a photon with a frequency of 6.0 times 10 raised to power 14 Hz. We are given that frequency F is equal to 6.0 times 10 raised to power 14 Hz. Now what we are going to do is, we now say, since it is frequency that is given to us, then we use the formula E is equal to HF. Now we put everything, we know our H, which is Planck's constant. It is constant 6.626 times 10 raised to power minus 34. This is the Planck's constant. Now we multiply it by our frequency, which is 6.0 times 10 raised to power 14. So when we multiply these two things, whatever it gives you is the energy of the photon. That is the answer. Now let's solve another example here. I have another question that says, calculate the energy of a photon having a wavelength of 10 raised to power minus 10 meter. Calculate the energy of a photon having a wavelength of 10 raised to power minus 10 meter. Here, instead of frequency, we are given the wavelength. they say that wavelength is equal to 10 raised to power minus 10 meter. That is the wavelength of this photon. So energy in this case, we are now going to use the second formula, which is E is equal to hc over lambda. We now put everything. We have h, which is 6.62 times 10 raised to power minus 34, then times c is velocity of light, which is 3 times 10 raised to power 8, 3 times 10 raised to power 8. Now we divide everything by the wavelength given to us, which is 10 raised to power minus 10. Now when we divide this, whatever it gives us is the answer. So this is how to calculate the energy of a photon depending on what is given to you, whether it is frequency or the wavelength that is given to you. Now let's talk about alpha decay. In alpha decay means where a radioactive element or a radioactive particle gives off helium atom. It gives off helium atom. In this type of decay, the radioactive element, the atomic mass is reduced by 4 and the atomic number is reduced by 2. In alpha decay, the atomic mass of the particle that is decaying is reduced by 4, while the atomic number is reduced by 2. Anything that gives off helium atom will reduce by these numbers, because helium, He, it has atomic number of 4 and atomic mass of 4 and atomic number of 2. This is helium atom. So anything that gives out or that gives off this helium atom is removing this helium from its nuclei. So that means you remove 4 from the atomic mass and remove 2 from the atomic number. Now let's look at an example of this. We can be asked to calculate. There is this question where we are asked to calculate. We are asked to calculate. Okay, they say that a nucleus undergoes alpha decay. A nucleus undergoes alpha decay. That is, there is this particular nucleus or particle that undergoes alpha decay. If the initial nucleus has a mass number of 238, the initial nucleus of the particle has mass number of 238. Now we are asked to calculate the mass number of the resulting nucleus. When after it has decayed, calculate the mass number of the resulting nucleus. Now let's call that particle A. Let's say that it is A. The nucleus of this atom A is what is decaying. Now this A, in its original form, the atomic mass is 238. Now let's say that it decays to form another atom, B. Now this B, and it has to give off alpha particle, that is helium atom when it decays. If it decays according to alpha decay, it must give off helium atom, and helium atom is He42. Now, what it means is that for you to get the resulting mass number of this B, you have to remove 4. You have to balance the equation by removing 4 from this 238. So if you remove 4 from 238, you now have 234. So the resulting nucleus, we have a mass number of 234 in order to balance this equation. So this is the answer. The answer is that the resulting nucleus, we have a mass number of 234. This is it for alpha decay. You can be given any element or any atom. Then once they tell you that it undergoes alpha decay, it means that a helium atom must be subtracted from it. So whatever that is remaining is the resulting nucleus. So anything at all that is given to you, just note that you have to remove helium atom from it, which is atomic mass must be reduced by 4 and atomic number must be reduced by 2. Then whatever it gives you is the resulting nucleus. Now let's look at beta decay. For beta decay, a beta decay is a radioactive decay, in which an electron is given off. In beta decay, an electron is given off. And one thing about beta decay is that the mass number remains the same, but the atomic number will change. If you noticed, in alpha decay, both the atomic number and atomic mass, both of them will change. But in beta decay, only the atomic number will change. The mass number will remain the same, because it is only the electron that is given off. So the other 10 remain the same. Remember that in nucleus, the mass number is equal to the number of proton plus neutron. Now in this case, the proton is not given off and neutron is not given off. All of them remain the same. It is only electron that is given off, and electron is what determines the atomic number. So the mass number remains the same because neither proton nor neutron is given off. It is only electron. So mass number remains the same, while the atomic number will change. Now let's look at an example. Let's see a question where a decay undergoing beta decay is solved. They say, how many beta particles are emitted in radioactive decay of this reaction? We have gold. Gold is Au, which is formed from mercury Hg, and they say that it undergoes beta decay. So gold is here 198, and we have 78 here, and mercury is 198, and we have 80 here. Now they are asking us how many beta particles are given off in this reaction. Now we balance it by removing electron from here. So we now say that if this is alpha particle or alpha beta decay, if this is a beta decay, then there must be electron given off, which is the first electron if this mercury gives out the first electron, it will become 79. So it will have to give off another electron to become 78, to change the atomic number to 78. So in this case, 2 electrons are given off. 2 electrons are given off to form this gold from mercury. So any other atom can be given to you, and once they tell you that it is a beta decay, you just subtract an electron from it, and when you subtract an electron from it, you are removing or reducing the atomic number. The atomic mass will remain the same. So this is how to solve this one. Now let's look at half-life. The half-life of a radioactive element or radioactive particle is the time that it takes that particle to decay or to decay into half. That is for half of it to remain. The time that it takes half of it to remain is the half-life. For instance, if they say that the half-life of a particle is 5 seconds, it means that after 5 seconds, half of it will remain. Assuming that the original mass is, let's say, 10 kilograms, then it means that after 5 seconds, half of this 10 is what will be remaining, which is 10 divided by 2. Half of it, 10 divided by 2, which is 5 kilograms, will be remaining. If the original is 50, then it means that after 5 seconds, it will be 50 divided by 2, which is 25. Now, let's look at an example from a past question. We have this question that says, a particle of radioactive material contains 100 atoms. A particle of radioactive material contains 100 atoms. So let's say that the original particle, we have 100 atoms inside it. Then if its half-life is 20 seconds, the time taken for 125 atoms to remain is what? Now they say that this particle, it contains 100 atoms. 1000, sorry, it contains 1000 atoms. Now they say that half-life, which is T half, is equal to 20 seconds. Now they say that the time taken for 125 atoms to remain is what? We should calculate the time that it will take it to decay to remain only 125 atoms out of the 1000. So let's call that number, the final number, n. Remaining is 125 atoms. Now, how can we calculate it? Now, original atom, we have 1000 atom, and half-life is 20. Now, it means that after 20 seconds, the 1000 atom that's originally present in that particle will become half. So after 20 seconds, we have 1000 over 2, which is 500. Then after another 20 seconds, we have 500. This one remaining here now will divide into 2 again. We have 500 over 2, which is equal to 250. Now after another 20 seconds, this 250 will also divide into half. We have, after 20 seconds again, we have 250 divide by 2, which will give us 125. So this is the number that they say is remaining, 125. So we now check the total time that it took it to get to this 125, which is 20 plus 20 plus 20. So the time it takes it to remain 125 atoms is equal to 20 plus 20 plus 20, which is equal to 60 seconds. So the answer is 60 seconds. 60 seconds. Now let's talk about energy levels.